Electrodynamometer type instrument. It is somewhat same as PMMC, permanent magnet moving coil. So as you can see, current is passing from here. This is a coil. This is a coil. This is go into this coil, moves out. So these two coils are our fixed coils, and this is a moving coil. It moves. Okay. So as you can see, the working principle is same as the PMMC, as I said. That is, whenever the current is applied and the conductor is in it, a magnetic field is created, and when the conductor is in it, it faces some force, and due to this force, this deflects. As you can see, with this moving coil, the pointer is attached. That is, a pointer is attached. That is, this deflects. So it deflects. So the basic principle is current is passed through it. So the magnetic field is created due to the mutual induction. This deflects. What is this mutual induction? This is the coil. There is some induction in this coil, and this is also a coil, highly resistive, so that overheating doesn't take place. And here also induction takes place. Between these two, mutual induction takes place. So basically current is passing through this, magnetic field is created, and this suppose acts like a spring, moves up and down. So as it is in this position now as it varies, so it will change and it will deflect. So this is our basic working principle. Advantage: there is no eddy loss. Why no eddy loss? Because no iron core is present. Initially iron cores were there, so eddy loss took place. Another advantage over PMMC in this is, in PMMC only DC was used, in this AC DC both are used. Disadvantage: the weight is it is really heavy and it is delicate as well. Now let's come to the torque equation. So as you can see, as I said, there is a mutual induction between this coil and this coil. See, this coil I am taking as same. These are two fixed coils and this is a moving coil. So I1 is the current which is passing through, suppose, the fixed coil, and I2 is the current through the moving coil. Okay, and these are two inductions in the fixed coil and the moving coil. Current is passing from here, current is passing from here. This is I1. In this, I2 current is generating, and this is I2. So this is our mutual inductance. L1 is the inductance in this fixed coil, L2 is the inductance in this moving coil. There is a mutual induction taking place between them. For the process is really easy. We calculated the flux linkage in the first coil, that is this one equals to L1 I1 plus Mi2, and this L2 I2 plus Mi2. The E1 is ddt of this, and E2 is ddt of this. The second part is a heavy calculation only, nothing else. Input energy. This is the flux linkage. Input energy we calculated, and that is the supply voltage. In the last case, in the last video you must have seen supply voltage we calculated. Here also EIDT is the supply voltage. So since there are two coils, I1 is there, and for the second I2, same for L1, L2, E1, E2. Okay, so these two, when they are further calculated, at the end we get this huge expression. That is, we just are breaking in this. You can just pause the video and check on the calculation. I'm just telling you the steps. You calculated the input energy. Next is the stored energy in the magnetic field, half Li square. Here L is 2 and I is 2, that is L1 L2, I1 I2. So two cases, plus the mutual inductance that is taking place, I1 I2 into M. So the change we can calculate: input, that is the initial state, and the final state. The difference we calculated, the change in the stored energy, this minus this or this minus this, and we get a huge expression again like this. Again you can pause and have a look over this. Now from the law of conservation, supply voltage equals to change in stored energy plus the mechanical work done. What is this mechanical work done? That is the, due to all this, the mechanical work that is doing, this is deflecting, so that is the deflecting torque. it is that. So we can say mechanical work done equals to change in supply voltage minus change in the stored energy. Okay, this is a change in the stored energy, this is supply voltage. We calculated this is supply voltage. When we subtract both of them, we get the value for mechanical work done, that is deflecting torque tau d, which is came as I1 I2 dm. Here you can see other things are constant, so we are not considering them, we were just taking I1 and I2. Now the deflecting torque, we can say this, and to counterbalance the deflecting torque comes the controlling torque tau c, that is proportional to theta. Theta is the deflecting angle, proportionality goes, k comes, tau c equals to k theta. At equilibrium k theta equals tau c equals to tau d, so k theta equals to this d by d theta. No, this theta came this side, so k theta equals to d by d theta. And again, since I1 and I2 are equal, yeah, I just mentioned it here, I1 is equals to, that is the current in the fixed coil is equals to the current in the moving coil. So theta equals to I1 I2, that is I1 square by k dm by d theta. So this is our expression. Thank you.